firing a bullet at a block attached to a coil. A rifle bullet with mass 8 grams strikes and embeds itself in a block with mass 0.992 kilograms that rests on a frictionless horizontal surface and is attached to a coil spring. As you can see in the figure, this bullet will come and get embedded in this block. The impact compresses the string 15 centimeters. Calibration of the spring shows that a force of 0.750 newtons is required to compress the spring 0.250 centimeters. Part A, find the magnitude of the block's velocity just after impact. Part B, what was the initial speed of the bullet? Now, from the calibration of the spring, we can see that the spring force magnitude, which is equal to K times spring constant times the change in its length, will be K times 0.25 centimeters, 0.25 10 to minus 2 meters, which gives us 0.75 newtons. Therefore, the spring constant K is 300 newtons per meter. So we can read it from this calibration data. Okay, so let's start with part A. Now, when the spring is compressed, uh, 15 centimeters, there is potential energy stored in it. The potential energy stored will be 1/2 K delta X squared. So with a spring constant of 300 newtons per meter, a delta X of 15 centimeters, 15 10 to minus 2 meters, we will obtain a potential energy at 3.375 joules stored. And this is happening on a frictionless surface, so we have no friction. Therefore, we can talk about conservation of mechanical energy. The system is isolated. So the change in the mechanical energy of the system during the process should be 0. So delta K plus delta U will be equal to 0. So delta K will be equal to minus delta U. So final kinetic energy minus the initial kinetic energy is initial potential energy minus final potential energy. What is the total mass? The total mass is 0.008 kilograms plus 0.992 kilograms, which is 1 kilogram. So final kinetic energy will be 0 when we have maximum compression. Initial kinetic energy will be 1/2 m total, the speed of the block right after the impact squared, which is equal to initial potential energy relaxed spring is 0 minus final potential energy 3.375. So this gives us for the final speed of the block, which is right after the collision, to be 2 times 3.375 divided by the total mass 1 kilograms, which is 2.60 meters per second. Okay, so now we're going back to the collision process. So this is all happening after the collision. Now during the collision process, net external force acting on the system is 0 on the system of the block plus the bullet. The bullet is embedded in the block system during impact. Okay, so this is basically a perfectly inelastic collision. So we can say that linear momentum is conserved, but energy is not conserved, and this implies conservation of linear momentum. So the change in the total linear momentum of the system must be equal to 0, which means the initial linear momentum must be equal to the final linear momentum. Mass of the bullet times its initial speed in I-hat direction is equal to the total mass final speed in I-hat direction. So from this equation we obtain the initial speed to be the ratio of the total mass to the mass of the bullet multiplied by the final speed, which is the total mass was 1 kilogram, mass of the bullet was 0.008 kilogram times the final speed. So this gives us, because we know the final speed is here 2.6 meters per second, for the initial speed of the bullet 325 meters per second. Okay, so in this process we have a frictionless surface. This block is attached to a spring. The spring is relaxed. And when this bullet comes and hits this block, it gets embedded in it. A perfectly inelastic collision occurs. Kinetic energy is not conserved, but linear momentum is conserved. And after the collision, the system of the bullet plus the block will compress the spring, because they will have an initial kinetic energy which will be stored as potential energy in the spring when we reach maximum compression. So a calibration data for the spring is given. A force of 0.75 newtons causes a compression of 0.25 centimeters, which gives us the spring constant. So in order to find the magnitude of the block's velocity just after the impact, we use the fact that we have conservation of mechanical energy for the process where the bullet plus the block is compressing the spring. So its kinetic energy is turning into final potential energy stored in the spring, which is 1/2 k compression, amount of compression squared. And the change in mechanical energy is 0 because there's no friction, so delta k is minus delta u. So we find that from the initial kinetic energy of the system, the final speed of the block plus the bullet was 2.6 meters per second after the impact. Now we go back to the impact, where we have no external force acting on the system. Perfectly inelastic collision. We have conservation of linear momentum. Total linear momentum initially was mass of the bullet times v0 I hat, because this was at rest. The block was at rest at the beginning. And then we have the total mass times the final velocity, the final linear momentum, which we can solve to find the initial speed of the bullet.